So, good morning. My name is Gianna Reginato, and I am an associate researcher at the Institute of Organometallic Compounds at CNR in Florence. Um, the Institute of Organometallic Compound is a part of the Department of Chemical Sciences and Material Technologies department, and is mainly is constituted by three different units. One is located in Pisa, one is located in Bari, and the main quarters of the institute are in Florence, in the research area of CNR in Sesto Fiorentino. ICOM is in Florence and is very strongly related with issues that are concerned with renewable energy, green hydrogen production, new fuel cells, the study of new fuel cells, innovative photovoltaics, heat storage. There are also other issues, but these are the most important concerning the project we are discussing today. Our contribution is mainly in WP4 and is mainly for materials for photovoltaics. The work is done mainly in a group which is called LEAF Lab, which is the acronym for Light to Energy and Fuels, and is mainly made by researchers which are concerned in organic chemistry. So we are all chemists, all working in the field of organic synthesis. But in the recent years, we have been mainly devoted to the study of materials, organic chemistry applied to the preparation of materials for the renewable energy exploitation. And we are the group is here in this picture. There were 6 permanent researchers and many other young researchers which are collaborating with us. And our contribution in the field that we are discussing today is mainly in the area of dye-sensitized solar cells, luminescent solar concentrators, perovskite solar cells, dye-sensitized photocatalytic hydrogen production, and also we are as we are synthetic chemists, we are very much interested in developing procedure which are concerned with green chemistry, which is maybe one can think that it's less urgent, a less urgent topic, but this is not indeed true because the kind of methodologies you use are very important for the whole sustainability of a process, and so also this part, which is more, let's say, less practical, is indeed very important, and I'll try to explain better this concept in the next slides. In WP4, we mainly contribute taking into account the experience we have developed recently in the field of dye-sensitized solar cells. We have been doing a great part of work in the last year in this area, and we are able at the moment to prepare and characterize small-scale photovoltaic DSSC devices that we produce in our photovoltaic laboratory. These are mainly test cells, but we can optimize all the materials which are necessary for the preparation. The main topic we have been working concerning this DSSC exploitation are in building integrations, in agrivoltaics, and more recently we are working for the optimization of materials for indoor application. To understand better the contribution we are trying to give in the project, it is interesting to remind how ESSC works. Very, very briefly and very simply, you can imagine a DSSC made by two glass electrodes, which are made of glass, of conductive glass, and in one of the two electrodes, one of the two electrodes is normally covered with a transparent layer of a semiconductor, very often titanium oxide, and on the semiconductor, a sensitizer that must be absorbed. In the presence of light, the sensitized is excited, and that means that an electron jumps from the from the ground state level to an excited state, and if the energy of this electron is good enough, this can be which means is higher of the excited electron is higher of the conductive band of titania. This can be injected in the titania and then going through an external circuit, go to the other electrode where using an electrolyte as carrier can be reduced and close the cycle. Why it is important, this mechanism? Because as you can see, electrolyte and sensitizer are key components of this device, and one of our most important contribution in this field is mainly due to the sensitizer. So we are really interested in study and optimize the sensitizer and in modulate the properties of these molecules depending of the kind of application we want to do. So also to understand which are the advantages of using this system compared with the traditional ones, as you consider the mechanism, you understand also that the cells is a very simple system made by glass, titania, the dye, the electrolyte, there is a gasket to put the two electrodes together, and there is a contour electrode, which is always in glass. So the aspect is very, very simple. And here you can see a small test cell we can produce in our laboratories, but you can see also bigger one, and you can see that they are very light, transparent, can be colored. So they have a lot of properties that that traditional photovoltaics don't have. In our laboratory, as I told you, we are equipped to prepare test cells without and to characterize them completely. We have high-speed mechanical mixer and ultrasonic probe for screen printing passes. We have a semi-automatic screen printing machine for the deposition of semiconductor thin films. We have programmable heating place for electrode treatment and hot press for cell sealing. In this way, we can prepare electrodes, but we can characterize them spectroscopically using UV visible spectrophotometer with integral control and integrating sphere, and a spectrofluorimeter with the same characteristics. And finally, we can prepare the cells and characterize them with a solar simulator and source meter unit for electrical and electrochemical characterization. So that means that at least to test the properties of our cell, we are completely autonomous and we can prepare the systems and understand whether they can be suitable for further utilization. Here is just a small movie to see how the laboratory works. You can see we have the screen printer and we can decide the shape of the cells. These are the small test cells who have been conditioned, and then the staining with all the dyes we prepare, and the final aspect the cells have, and the characterization under the simulator, and the preparation of the current potential curves. So all that because in view of our of this experience, we have been interested in participate to the system, um, studying materials for photovoltaics, especially in the area of development of devices for production and of energy and its storage. That means that we are working especially in the development of photoelectrochemical energy storage devices able to convert and store solar energy in one to electric factory. This is interesting because this kind of batteries have simple configuration. Probably they are going to, once developed, to cost less, and probably they will be easy integrated. The importance of this system is that the photo-generated charges are used directly for the accumulation. So, as you have already seen from my colleague Nicola Sangiorgi, the preparation working in FENSA at ESSMC, the development of devices is mainly interest of the group of research, but our contribution is in development of photoactive materials for having efficient photoelectrodes. So you understand how our experience in the field of the SSC can be used for this kind um, of systems. So, arriving to what it is really our main work, we are interested in developed new photosensitizers for this special application. We are working in the field of organic dyes. So we propose in the project structures with our pure organic dyes, which have never been applied in this kind of systems before. Why we propose this kind of systems? Because they have some interesting advantages. First of all, they don't contain metals, so they are quite sustainable. They are characterized by having an intense light absorption. They are normally easy to prepare, but especially to purify, using scalable and modulable synthesis. This allows to modulate the photo and electrochemical properties, and they are generally quite stable. Just to schematize the systems without going in, but we will see some molecules, but not so many. But what I want to show is that this kind of molecule can be schematically represented as group as three main principal group. One is a donor, which means that it's rich of electrons. In the middle, we have a spacer, which means that allows the communication of the electrons from the donor to the third element, which is an acceptor, which is a low element which attracts electron. The acceptor generally is also able to link to the titania and allow the electron injection. So if you remind how it works, the DSC, you understand that this kind of molecule can be variated in order to make the process of light capture and electron injection as productive as possible. As you can see, these kind of molecules are also called as push-pull systems because they push the electrons from the donor to the acceptor and then inside the titanium. Here you see the first molecule of this slide. There will not be very many, but it's just to see that if you divide this system, you can see where is the donor, where is the scaffold, and where is the acceptor. And the main characteristic of the system is that you have to let the electrons flow from the donor to the acceptor. It is interesting to see that if you change any of these single element of the molecule, you can change the properties of the molecule. And so you can direct these properties in the direction that you prefer depending of the application you want to do. The other very important point is that these characteristics can be predicted by theoretical calculations. So I can, on principle, draw a molecule and understand, go to see whether it can be suitable for the application I want to do. Starting from this point, we have proposed for the project six different structures of organic photosensitizers, which were selected by taking into account several properties. The most important are to have an intense light absorption in the visible region, to have electrochemical parameters suitable for allowing injection process into titania, as I show in the mechanism is very important, but also dye regeneration using several different electrolytes because otherwise the process doesn't occur. Finally, they have to have a stable anchor to titania. So these are the molecules we have proposed. We are not interested in see the single, the several, how they are done, but what I want to show is our approach. The approach is that to keep some of the part of the molecule, you see these here in green, the same, and to change only small parts to see how this changement affect the final properties. And this is quite important because as we have to prepare these systems to have a modulable structure allows to make the synthesis more easy. In particular, we have proposed, as I told you, six different systems. One is the one I showed you before. There are these other, which are the TTZ series. These acronyms are simply a way that we use to underline the main scaffold of the molecule. So TTZ means thiazole. So it is just this small part of the molecule, or BTDDPT, which means this benzothiadiazole dithienopyrrole. So these violet systems are of the same series, which is what is important to understand, and are different just because in one case you have something in between which is different. So these small modifications change the properties of the system. And what we want to see it is how they change and how they affect the final system. So here also, as we are synthetic chemists, the synthesis is a big part of our work. So these six molecules we have chosen, we have to prepare. Also in this case, I want just to show the approach we use. The approach is very modulable. And what we do is like to divide these molecules in some different puzzle part, And so you can imagine this is the final one. This is the green part is the acceptor. The yellow part of the puzzle is the scaffold. The red part of the puzzle is the donor. Oh, sorry. And we have just to prepare any single part, any single part of the puzzle, and then find a good way to put them together. This is this is interesting because we we can, as I show you before, use different part. I mean, this yellow part I can use on a different scaffold. So this is a very modulable system because with the three single card of the puzzle, I can make many molecules. This is the way we have built up the BTD-DPT series. This is the way we have built up the TTZ series, but as you can see in both cases, we are just finding a way to put together the small pieces of the puzzle. And simply changing one of these pieces, I can change the properties of the molecule. The only other thing I want to say concerning this point is that, of course, every single step of the preparation has to be optimized, which is what we have done on all these six molecules. And every reaction pathway has to be studied in order to get the best result. But we do something more. What we do it is also to try to have an eye on a green synthetic approach when possible. A green synthetic approach means that we not only try to have the best result, but also to find a way to do the preparation in a sustainable way, which means trying to reduce the energy demand of the reaction, trying to reduce the waste produced in the reaction, trying to replace hazardous chemical with safer alternatives. And this is what we try to do also in the context of this project. In fact, for example, for some of these molecules we have prepared, we have been able to optimize the process using non-toxic reaction media and using very efficient protocols like substituting the cross-coupling reaction we use normally, which are metal depending, palladium catalyzed, with the processes of CH activation, again palladium catalyzed, but with a big reduction of waste. I don't go in details here, but I am ready to do it if someone is interested to go more in deep. Finally, the sensitizer once have been prepared are characterized, as I showed you before. So we do the spectra, we do the UV visible spectra, we do the cyclic voltammetry, both to see whether we have a good absorption on light, and if the dye can be easily regenerate by the electrolytes we are using. And I have to say that all the dyes we have prepared show an intense light absorption in the visible region and have electrochemical parameters which show which that can be probably easily regenerate. As you can see, the absorption has changed with the structure, having a best absorption, for example, with TTZ9, and also having a very good, which has also a very good regeneration parameters. So what we do after is try to see whether we can really prepare the electrodes. So we test the anchoring capacity of the dye on the metal oxide. And so we have make deposition of nanocrystalline titanium films, and then stained with the dyes. In this case, it is reporter TTZ5. You see this very good, very nice orange-red color. And as you can see, the absorption, we measure the absorption on the electrode, which is still good, broader and blue shifted compared with the solution systems. And the other point, very important, is that with this, which are stable because the color is permanent and remains in time for a long time. We have also prepared some cells to evaluate if really these dyes, sensitizers, are able to transfer the charge to the semiconductor and to be really regenerated to the ground state. So we have prepared a small DSSC test cell and measured the PCE, which is indeed quite good for this system. And measuring, I think this one is a TTZ5. Yes, TTZ5, and we have a PCE of 7.4, which is quite good, and it is maintained with bigger cells and also with mini modules. So this data is also have also been published and confirm that this dye have good injection and can be used to prepare the electrodes, which is what we have done, because we have prepared our electrodes and sent to Nicola San Giorgi in Faenza, who is now trying to see whether it's possible to build the systems and which is the final efficiency of the whole system. So just to conclude, our contribution in the project has been that of prepare new organic dyes who had been never used for photo rechargeable electrodes, and uh, to uh, to optimize the preparation in the best sustainable conditions. And we have then produce and characterize the film for photo electrodes, and determine the photoelectrochemical properties of some dyes and semiconductor combination. These materials will be used in activities 411 and 412, and now are under study at the in CNR in Faenza. This is just a group to show you. We are six of us, but we have many young researchers who are collaborating with big enthusiasm with us. And with this, I close and thank you very much for your kind attention.